The Hausman test helps us choose between fixed and random effects models. In the tutorial on random effects, we discussed all the assumptions of the fixed effects as well as the random effects model. Remember, the critical assumption separating both the models is that the unobserved effects are assumed to be not correlated or uncorrelated with the independent variables in the random effects model. This assumption is satisfied when the individual and time-specific effects are uncorrelated with the independent variables. In such a case, the random effects model is asymptotically efficient and consistent. If this assumption is violated and the individual or time-specific effects are correlated with any of the independent variables, then the random effects model estimates are inconsistent. On the other hand, the fixed effects model is robust to this correlation and its estimates are consistent even when the unobserved effects are correlated with the independent variables. The Hausman test is based on this assumption and it compares the estimates of the fixed and random effects models. The fixed effects model is consistent either way, but the random effects model is consistent and efficient only if the unobserved effects are uncorrelated with the independent variables. If the random effects estimates are too different from the fixed effects estimates, then we know that the random effects model is inconsistent. The logic behind this is that the fixed effects estimates are consistent either way. So, if random effects estimates are too different, then we know that they are inconsistent and the critical assumption has been violated. On the other hand, if the estimates of both models are similar, then we know that the random effects is not only consistent, but also efficient. This will happen only if the critical assumption of no correlation between unobserved effects and independent variables is satisfied. Therefore, the hypothesis of the Hausman test for fixed versus random effects can be stated as shown here. Under the null hypothesis, the estimates of fixed and random effects models are not significantly different. Both fixed and random effects estimates are consistent, but the random effects estimates are also efficient. Therefore, we should prefer the random effects model. Under the alternate hypothesis, the estimates of fixed and random effects models are significantly different from each other. Therefore, only the fixed effects estimates are consistent, while the random effects model is inconsistent. Hence, we should prefer the fixed effects model. In R, we can use the pH test function provided by the PLM package to apply the Hausman test for fixed versus random effects. First, we have to estimate the fixed and random effects models using the PLM function as discussed in the previous tutorials. We will continue with the same example of fixed and random effects with individual specific effects only for the Grunfeld data. In the commands shown here, we first estimate the fixed effects model with individual specific effects using the PLM function and save the results in the within-ind object. Next, we estimate the random effects model with individual specific effects using the same PLM function and save its results in the random-ind object. Now, we can use the saved results to apply the Hausman test as shown here. In the pH test function, we first mention the fixed effects model saved in the within-ind object followed by the random-ind object containing the results of the random effects model. This function will report the test statistic along with p-value of the Hausman test. In Stata, we must also estimate and save the results of fixed and random effects models before applying the Hausman test. In the commands shown here, we first estimate the fixed effects model using the FE option of xtreg function. Then, we save the results using estimates store fixed. This will save the estimates of the model in the object named fixed. Next, we estimate the random effects model using the RE option of xtreg command. We save its results using estimates store random, which will save the estimates in an object named random. Now, we can apply the Hausman test using the Hausman command as shown here. We first mention fixed, containing the results of the fixed effects model, which is a consistent estimator. Then we specify random containing the random effects estimates, which is an efficient estimator under the null hypothesis. Sometimes, it is recommended that we specify the option sigma more. This option instructs the command to use the covariance matrix based on the estimated error variance from the random effects model. This can be useful in certain cases if the test produces a non-positive definite differenced covariance matrix. Either way, the results of the Hausman test are asymptotically equivalent whether we use sigma more, sigmaless, or none of these. The Hausman statistic is calculated using the formula shown here. As we can see, the test essentially compares the fixed and random effects estimates and the variances of these estimates. The H statistic is distributed as chi-square with degrees of freedom equal to the rank of the matrix containing the variance terms as shown here. In our Grunfeld example, we illustrated the fixed effects within model and the random effects model with individual specific effects. If we apply the Hausman test to these models to check whether fixed effects or random effects are appropriate, we get the results shown in the table here. The Hausman test statistic is reported as 2.3304 with degrees of freedom equal to 2. The p-value is 0.3119, which is greater than 0.05. Therefore, we cannot reject the null hypothesis and conclude that both the estimates are consistent, but only the random effects model is efficient. Hence, we should prefer the random effects model with individual specific random error. Thank you for watching, and I hope you liked this series of tutorials.